Good morning everyone. This tutorial is to tell you how trigonometric functions graph is not possible by taking mirror image about the line y equal to x. We know that for algebraic functions, except some rational functions, if we take the mirror image of the given function about the line y equal to x, then you get the graph of the inverse function. It is actually when you take reflection about the line y equal to x, we get it. But in case of trigonometric functions, I tell you, just the reflection about y equal to x doesn't give you the inverse function. If we take y equal to sin x graph, you all can see that it is maximum value 1, minimum value -1, and at these points the value of the function y equal to sin x is going to be equal to 0 when x equal to 0 pi. This is the line y equal to x passing through origin. If we take the reflection of the graph of the function y equal to sin x about the line y equal to x, the graph is like this. This cannot be inverse of this function. What I was telling you, this is the difference between the algebraic functions, rational functions, and trigonometric functions. Trigonometric functions are in a certain interval. It may be defined, but it is not one-on-one-to function. Inverse of one-on-one-to function only possible. For this, y equal to sin x, if you go through the graph, say -2 pi to 4 pi, if you go through, it's a many-to-one function. At many points, we get the same value of y for different values of x. So this function is not one-on-one to its inverse and not possible by taking reflection about this line. Similarly, if we make it for cos x. Cos x also, if you draw the graph, then it is not one-on-one to in general, but if we restrict the domain, then it will be one-on-one to, and its reflection about the line is not the inverse of the function y equal to cos x. So what you have to do there, you have to restrict the domain. If we try to get the graph of cos inverse x, see only smaller part of the portion. If we make this one off, let us make this one off. I mean that reflection what you told, it is going to be the inverse of y equal to cos x. I make that part off. Now truly I am getting the inverse here. This small part will be the inverse, but inverse of which part? That you have to understand. So we need to introduce the concept of principal value branch here. For cosine function, 0 to pi is the principal value branch. I mean from this point x equal to 0 to x equal to pi, if you go, then its inversion is there. Okay, at this moment I am just showing you how inverse is not possible here. That inverse of this whole graph cannot be this part. Okay, now let us go for y equal to tan x. Let us plot y equal to tan x. Again the same problem arises. This is many-to-one function over the number line, so its inversion in general not possible. But if we write an inverse x, only small part is given the inverse. It is not extending above. Then if I say that this is going to be the inverse of the whole tan x part, whole tan x graph, then it is wrong, because tan x function is a many-to-one function, so its inversion not possible. So just instruction if you send to find tan inverse x, it will give you the result, but this is not true one. We need to restrict the domain. For tan inverse x, it's going to be -pi/2 to pi/2. If I take the graph for this part only, other part we make absent, then we get the inverse. The same manner it happened in case of cot x also. This is the graph and this is the inverse. This is not many-to-one, its inverse and it's not possible, but GeoGebra will follow your instruction if you are giving the accurate instruction. Here the instruction is wrong. Here simply you are taking reflection about the line y equal to x. So the inverse you get here, this is not the inverse. Truly this is not inverse of this y equal to cot x. We need to restrict the domain. This time next section we are going to show you that it is for 0 to pi in that interval. I mean from this point to this point, its inversion we got from y equal to cot x. The cot x graph was from 0 to pi, its inversion in x. Let me show you the next GeoGebra graph, next GeoGebra work, where you will understand how to get the inverse. Let me open this GeoGebra file. In this file, we'll see how inversion of trigonometric functions possible. We have to restrict the domain. We have to consider a part of the domain of definition of the function. Then only inversion is possible. Let us do it for y equal to sin x first. Let me make all other graphs absent from here. I am doing it for sin x first. Y equal to sin x is the graph. This is not invertible. I told you in general this is not invertible. But if we restrict the domain, then it is going to be invertible. See how it is going to be invertible. The graph I have considered here. This is extending from this extreme point to this point, and it has maximum value 1, minimum value -1 for sin x. If I restrict the domain, if I draw the graph from -pi/2 to pi/2, make this one out. This function inversion is possible. This is the principal value branch. See, I am finding sin inverse x graph now. See, and if I plot the line y equal to x, then this is mirror image. So mirror image concept is fine. If the function is 1, 1 onto an interval, then mirror image about the line y equal to x will give you the inverse of the function. So for this graph y equal to sin x, if we restrict the domain from -pi/2 to pi/2, this is the thing, -pi/2 to pi/2. Its inversion is this thing. Okay, about the line y equal to x, it remains symmetric with the given curve y equal to sin x. Understood? So as you have restricted the domain of definition here, this is truly representing the inverse function graph y equal to sin inverse x. Let us go for cos inverse x graph now. I keep only this y equal to x line over there. Then let me plot cos x graph. But cos x graph again many to 1. Just the previous file I have explained. This is many to 1. Its inversion not possible. If we restrict the domain, then you can get. I am restricting the domain here. You can see 0 to pi I am writing. So this thing. Although equal to 0 and equal to pi also inclusive over there. So this is the graph of the function cos x from 0 to pi. Its mirror image about the line, if we consider, then we get the inverse function graph. Okay, y equal to cos x will be there, then y equal to cos inverse x. So blue one represent cos inverse x and this one represent cos x. Again you take mirror image about the line y equal to x. Mirror image of what? Mirror image of the original graph. This is cos x. This thing is going to be cos inverse x, which is the image of this thing. Okay. So this time inversion is done. Let us go for tan x. See, in the previous graph, I am repeating that part again. Tan x graph I am drawing again and again, just to keep in your mind that tan x graph, its presentation. Remembering tan x graph is important for you. So tan x graph you must keep, and then you will say that it is not one-to-one function. Its inversion you cannot get. But if we restrict the domain, -pi/2 to pi/2, then it is possible. So which part is here? Only this part. See, it has become thicker. I am making the original graph absent. It exists in the portion -pi/2 to pi/2. The tan x graph is invertible over there. Its inversion, let me draw. This is the inverse. It's very good to see that y equal to x again will give you the image of the original graph if the domain is restricted over there to write the inverse of the graph, inverse function graph. Okay. If you take a point here, say point I am taking a comma b here, on it there will be a point b comma a. There is a point c comma d here, there will be a point d comma c on it. It's like that. Original curve, if it is c comma d, it will be d comma c in the new one, and vice versa. Okay, so tan x part is done. Let us go for cot x function. Again the same manner, y equal to x I am keeping unchanged. Just let me draw cot x. As it is many to 1, its inversion not possible in general, so we should restrict the domain. It's 0 to pi. See, this function inversion is possible. We can get it inverse over the interval 0 to pi. How? Just write this thing. This is the inverse. This curve is the inverse. You take the mirror image about this line. See, this to this part has image here. Every time you'll get some image. This part no, this part no. About this y equal to x, if you take the image, this is going to be the image. Similarly, inverse of this part, its graph will be this one. Inverse of every part you can get this way. Okay. So let us go for other trigonometric functions also. You can play with these if you can download this in your computer. So for sec x, this is not invertible. Again the same reason, it is many to 1 function, so we should restrict the domain. This thicker part is becoming sec x in the desired interval 0 to pi. Here it is invertible, but at the same time you have to note pi by 2 cannot be in its domain of definition. See, pi by 2 did not show. Let me make the original graph apart from the graph in the domain of definition. This is sec x. About the line y equal to x, if we take the mirror image, the graph is obtained like this. See, every time you are getting the mirror image about the line of the original graph, you get the inverse. What is the mirror image of this part? This part mirror image is this one. Okay, this is the original graph. Its mirror image will be in this coordinate like this. Okay, so sec inverse graph you got. Similarly, we can do it for cosec x. Again, this is many to 1 function, inversion not possible. We are restricting the domain from minus pi by 2 to pi by 2. See, only this small part exists. The inverse of this is the mirror image about the line y equal to, this is really becoming inverse. About the line y equal to x, you take the mirror image, you got the inverse graph. Okay, so now we can draw a conclusion that for algebraic as well as trigonometric functions, if we get a function not many to 1, 1 on 2, then its inversion possible. And in that case, inversion can be obtained by reflecting the graph about the line y equal to x. Okay. Now let us go for finding the composite function. What composite function? Everyone has the idea that sin inverse sin x. Many students have told me, sir, sin inverse sin x, you are saying its value is x. And the interval you are telling that principal value branch if you write, then it's fine, we can write sin inverse sin x equal to x. How this is going to be changed if the interval is changed? See how the interval is going to be changed here. It's very good to see that interval we change, then also there exists the function, the inverse function. No, here the composition of function exists if we consider different part. Yeah. For y equal to sin inverse sin x, this is the genuine graph. But you don't have the right to say that y equal to sin inverse sin x equal to x everywhere. Normally it seems that sin inverse sin x means x. Cos inverse cos x is x. But there is a paradox that sin inverse sin x is not always x, or cos inverse cos x is not always cos x. If I consider the graph that sin inverse sin x, if I say that y equal to x, then y equal to x line will be this. This is line y equal to x, where it will intersect, that is the value of the function in the principal value branch. You know, for sin inverse x, the principal value branch is minus pi by 2 pi by 2. Here, the graph of the function is given by this, y equal to x. This is the line y equal to x. So, inverse of sin x, sin inverse sin x in this interval minus pi by 2 pi by 2 is going to be equal to x. If we go for the next interval, just I am erasing this part, go for next interval. See, this function is y equal to x minus 3.14. It is actually x minus x minus pi. So it has value minus x minus pi. Where? It has value minus x minus pi in the interval minus 3 pi by 2 minus pi by 2. You can explore the idea using GeoGebra every moment, because that previous one y equal to x was there in the principal value branch. Question automatically arises if we write minus 3 pi by 2 minus pi by 2, what will happen? So you can plot the graph between minus 3 pi by 2 minus pi by 2. If you give the instruction GeoGebra to draw it, it will draw the graph for you, which is minus x minus pi. And if we remove this one, let us go for next interval. Yeah, this one, see, I am taking one interval here, then here, like this. This is y equal to x minus x plus 3.14. In the interval, which interval is here? You can see the interval, it is pi by 2 to 3 pi by 2. Your answer will be between pi by 2 to pi by 2, sine inverse sine x is going to be minus x plus pi. It seems a bit different because sine inverse sine x in CBSE class most of you have done. That is going to be x only. But see, the value of function changes with the interval. Let me remove this part. Now going for this one. See, this is x minus 2 pi. X minus 2 pi where? Where it is invertible? It is invertible between 3 pi by 2 pi by 2. The graph of the function is like this. Next, let us go for another interval. See, let me make this. I have done already, so let me make this one absent. Go for this one. It was like this. Next interval, it goes this manner. Actually, this part of the graph will represent the inverse function. So, in the interval minus pi by 2 to minus 3 pi by 2, sine inverse sine x is going to be x plus 2 pi. Can you remember this way? Just placing the graph, it will be more convenient for you. And next one, make this one. See, in this interval, what is the interval? It is 5 pi by 2 to 7 pi by 2. The sin x graph is 1 on 2 over there. Its inversion is possible, and the inverse is given by this thing, that y equal to minus x plus 3 pi. And 9.42 is 3 pi almost. It's given this way. So you can do your experiment. You can explore many things for sine inverse, not only for sine inverse sine x, cos inverse cos x, tan inverse tan x. Their value you can decide from the graph only. So I request you explore yourself, invest some time with it, then you can understand better. Thank you. See you again.